So let's think more about eigenvalues and eigenvectors. Some people might have had them in an elementary linear algebra class, but forgotten. Some people, maybe their class didn't have time for them. So they're really important in lots and lots of applied math. We basically never find eigenvalues and eigenvectors the way you might have learned to do it by hand, which for me was very painful. I mean, mentally painful. We're not going to be worrying about that. But let's just talk about their properties. We usually only do eigenvalues and eigenvectors for square matrices. There might be a generalization for rectangular, but we won't worry about it. If you have an n by n matrix, it will have n eigenvalues. They might be repeated, just like the roots of a polynomial. In fact, eigenvalues are related to roots of the characteristic polynomial of a matrix. And eigenvalues can be complex valued. If any eigenvalue is 0, then the matrix is singular or non-invertible. And this is an interesting numerical fact. If the smallest eigenvalue is close to 0, and what does it mean to be close to 0? Well, you kind of compare it to the largest of the eigenvalues. Then the matrix is close to singular or non-invertible, rather than being exactly singular or non-invertible. Close to singular means that you're going to have a lot of round-off error if you try solving a system with it. We'll talk more about this whole thing about eigenvalues being close to 0 compared to the largest eigenvalue later in the semester. But it's interesting to know that in pure math, we say the matrix is either invertible or not invertible. In applied math, a matrix can be close to not invertible, and round-off error plays a role there. If you have a diagonal matrix, you just look at the diagonal and say, hey, there's the eigenvalues. And that's even true for a triangular matrix, whether it's like everything in the lower triangle and diagonal is filled in and the upper triangle is all 0, or vice versa. So we like those kind of matrices, but they aren't symmetric, so we also like symmetric matrices. The product of the eigenvalues is equal to the determinant of the matrix. That's kind of handy sometimes. And if the matrix is symmetric, all the eigenvalues will be real, which is a lot easier than when they're complex. So we really like symmetric matrices. It's a good thing our Hessian is basically always symmetric, isn't it? So how will we use all this eigenvalue, eigenvector stuff to determine whether a matrix is positive definite or not? Well, we said if we do q times h and get back a scalar multiple of h, like lambda h, before we called it a, but now that we're thinking eigenvalues and eigenvectors, we'll call it lambda. So if h is an eigenvector of q, then we'd get this. And if lambda is bigger than 0, then we'll have a positive number times a vector dot producted with itself, which is always positive, because h is not 0. And so we get a positive number. So if the eigenvalue is positive, then HQH is positive if h is the eigenvector for that eigenvalue. What if lambda is negative? Well, then you get a lambda less than 0 here, and you'd always get negative numbers. So if q has any negative eigenvalues, then this product is not always bigger than 0. So then q is not positive definite and not positive semi-definite. You might say, why do we keep picking directions that are eigenvalues, eigenvectors? There's lots of directions that aren't eigenvectors. Turns out you can write a direction as a sum of weighted eigenvectors usually, and just do a bunch of algebra and it all works. So apparently eigenvalues being positive or negative makes all the difference in being positive definite or negative definite. So overall we can say q is positive definite, and remember q is a square matrix, if all the eigenvalues are strictly positive, positive semi-definite if some of the eigenvalues are 0 possibly, or maybe all of them are positive. It's indefinite if some eigenvalues are negative and some are positive. It's negative semi-definite if all the eigenvalues are less than 0 or less than or equal to 0. So the obvious thing for negative definite there. And we should fix that. Now you might be saying, I don't want to go find all the eigenvalues of a matrix, and I totally understand. There are computer routines that can do that, and that's great. But another way of quickly checking whether a matrix is positive definite or not is called the principal minors test. So you take the determinant of the whole matrix, and if that's positive and the determinant of each square submatrix stacking up toward the corner here is also positive, then overall the matrix is positive definite. And you can kind of see the relationship there because we're talking about determinants, which are products of eigenvalues, and if the eigenvalues are all positive, then all their products will be positive. And if we're checking each submatrix, then we can't have like two negative eigenvalues that cancel each other and give a positive. So that's the principal minors test. And you might say, so let's repeat it. If all those principal square submatrices have a positive determinant, then the matrix is positive definite. If some of the determinants are zero, then the matrix is positive semi-definite. What about negative definite? You might expect them to all be negative, but life is complicated and they would actually alternate in sign. Or what you could do is just multiply the whole matrix by -1 and check for it being positive definite. So maybe it's a little clear now where the second derivative test in Calc 3 comes from. The second derivative test is that the determinant of this 2 by 2 matrix is positive, which is this times that minus this times that, and that this first element is also positive. So that's just the first principal minor and then the main Hessian matrix of a two-variable system. So that's it for all our eigenvalue and eigenvector stuff for now. We'll see them later in the course. But we're not going to move on to what seems like a completely different topic about convexity of sets in the next batch of videos.